Hi, so we're back with another, and we're going to let's do a recap of what we did last time. So last time we discussed that again. Let's just go back and see what we had discussed in these slides. Today will be the end of this, the slides shown in the first lecture. So let's just do a recap of what we have studied. So we started with how database systems are just files on disk, and then we looked at how sequential writes and reads are beneficial for modern SSDs and the HDDs that were back in the day, and how sequential reads, like the your storage manager can efficiently read and write to the disk once your reads and writes are sequential. So then we started looking at database systems layer by layer, that we have an execution engine that has the logical representation of data, that has some sense about tuples and what their human representable form is. And then we saw that down the layer we have a buffer pool manager, which serves as a cache for our database system. That's like the data that is lying on disk. And then we have a disk, which serves as a primary storage location. Then we started looking at that how pages are fetched, how database is divided. That databases, you can define particular directories, or you can have one directory or one file, and you can store your entire database in one file. Or what you can choose to do is you can have multiple files for, let's say, you can have files for tables, files for a particular database, files for a particular index. You can just your it depends on how you design your system and what freedom you are giving to the user. User in this case would be the application, the backend application that is contacting your database. So then we saw that how database system is divided into files, that you read a database file, and then we saw that how a file is divided into pages and how those pages are stored on the disk. You can then we saw that there are different storage mechanisms, like you can use heap file storage or tree file storage, or you can use a hash table, hashed storage, where you would hash your keys and then you would find particular pages to store those keys. And we read about heap file storage, that how it is unordered, and we need to maintain higher level B trees indexes to index into that file and to have some order about the data. Or every time you do a scan, you would be doing a sequential scan. Then we discussed a bit about tree-based structures, that how tree-based structure gives some order to files, to page storages. Then we started looking at the page itself. Then we saw how pages are laid out. Then we started with the layman technique of just writing appending tuples. Then we saw that how fragmentation was an issue there. And whenever I moved some tuple, I have to notify the above level, like higher level indexes, that yes, this location has changed and you need to point to some other physical location. Then we also saw this particular slide, the slotted pages technique. Now, what is done in this technique is a slot array is maintained at the start of the page and tuples are appended from the end. So the slot array, everything above outside the page points to the slot array, a slot in the slot array, and the slot array points to a tuple in the page. And what benefits this gives us is that inside the page, I can reorder the page, I can run vacuum, I can uh, compact things, I can delete things. My higher level indexes, anything pointing to my particular page, doesn't have to be notified because they are still pointing to the slot array. And within the slot array, I can change the offset of the page. That yes, now this tuple is moved here and that tuple is moved there. So we saw how this approach worked out well. Then we also said that each tuple is identified by a record ID. We also did a demo for this on Postgres, that it has a CT ID, and we saw how pages were being switched and how each page could store a bunch of data. Now we are up to a point where we have covered file storages, page layouts, and now we are in the tuple layout. So in today's lecture, we are still going to study tuple layout. So, database, as I drew last time, that databases are just files on disk, and uh, each file has pages. Each file is divided into pages. So we saw how pages are laid out, and there the page ordering is what heap file and tree file organizations cover. And then we looked inside the page. That's where your slotted pages come in. And now we are looking at at a very molecular level. We are looking at the tuples. That how inside a page tuples are stored. So now to start with the tuple layout, each tuple begins with a header. So whatever your data you store, there might be a header. There's always a header which stores a checksum that it might contain checksum and other schema information. If you would like your tuple to be self-contained, you could also store your schema there. But most of the database systems don't do that. And you can like store other metadata about it, or you could also store null bitmap, that what fields are null. So we'll also talk about nulls towards the end, I guess. There are a couple of slides on null specifically for nulls. So yeah, there is the uh, header at start of every tuple, which gives us some idea of what's inside the tuple. Again, different database systems do all kind of things, that they store different things in the header. So as I said, the header might contain visibility information like Postgres stores tmax and tmin. That is for doing their MVCC, that what transactions should be able to see what version of the tuple. So that's how they do concurrency control in Postgres. And Postgres might be keeping data around for longer than what is required. So they might have duplicates of the same tuple, and different transactions running in the system might be looking at different versions of that same tuple. So that information might be stored in the header, that for concurrency control, what transactions can see what. Can this transaction see this particular tuple or not? Then we talked about that how bitmap might be stored for null values, that if you, let's say you have five values in your tuple and you're storing a bitmap of 5 bits, and you flip the bit to 1 if it is not null, and you keep it to 0 if it is null. You might do that in the headers. But yeah. There's also a statement that we do not need to store metadata about the schema. You might, if you're designing a bad system, you might, but usually those systems don't do that. So for self-contained pages that we talked about, the schema might be stored in the page header. So Oracle or MS SQL do this to make the pages self-contained. That if you have some disaster that your metadata pages have been lost, you can still read data out of the data pages. So, but nobody stores schema information inside the tuple. So imagine you have like 100,000 tuples and you would just keep replicating all the schema information in that. So that is wasteful. So let's talk about tuples. Tuples are nothing, just appended bytes. So let's say you're defining a table. Let's say this is a food table, and you're defining attributes in that: A, B, C, D, E, F. And at the end of it, database system will not do nothing but just serialize these bytes to disk representable format and just write them out to the page. So in the end, you have something that starts from byte something. I'm just taking an arbitrary number, 0xa, and it's ending at somewhere around somewhere. Right. So it's just byte representable form of data. So it's nothing but just bytes lying out on the files. So, in this particular case, we're looking at data is that like I can define a table, and when I insert a tuple in that, I can just take that raw data and I can just write it out to disk as bytes. But then again, I would have problems, right? Because NDNS might make a problem in that, that I'm writing for systems that are portable. Let's say MySQL, sorry, MS SQL, not MS SQL, sorry. The systems that might be portable, that are portable, like SQLite, what they do is they define a particular order, that NDNS, that they will follow for their entire system. So let's say I have a Mac-based system, and like I have a Mac-based system and I run SQLite. So SQLite will write my data out to disk in big Indian format. So if I pick that up and I run it in some system that is Little Indian, that would that would expect that the particular database file has its bytes written out in big Indian format. So Indianness might not be an issue in that, but in systems like Postgres and my MS SQL, MySQL, this might be a problem that the tuples that might work on one machine might not work on a machine with different NDNS. So, so tuples are nothing, just laid out array of bytes on disk. So as we can see here, like this particular thing, we have a tuple which has a header, and then we have a array of unsigned characters. So there is no sign defined on that. So it's a just think of it as a byte array that is lying on disk. And in the header, I'm storing that how long is this byte array? And when I read it out to from the disk via the storage manager, it throws it out to the execution engine, which then makes sense out of it. That how many offsets I need to read so that I can figure out where ID is, and then to figure out where value is, and then I break down values to their specific column names. And then I read schema information from some other page to just figure out that how do I make sense of this value, because this value is itself a byte array. So I need to break these byte arrays into chunks so that I can read, like, let's say name or email or phone number. So each tuple has an ID. So each tuple is defined by a primary ID that you define, or the database system might just generate its own internal IDs. Like SQLite does it. No matter what primary key you give it to SQLite, it will always generate an internal ID for every tuple. So your primary key is kind of the index you make on a primary key is kind of a secondary index that you are making. It's not the only starting index that you have. So the internal record IDs that SQLite maintains, SQLite makes a B-tree index out of that. And your primary key index that is looking like a primary key index to you is pointing to that particular record ID tree. So yeah, it's showing that how it's an example that C++ function that you can reinterpret cast the particular address. Like if you are reading this whole thing, let's say I've read a whole page into the buffer pool. This is my buffer pool, and I have frames in this buffer pool where I want to fill pages. And I have read this particular page. Then I would just, if I'm writing my system in C++, I would just use this function and pass the address to some offset in the page, and then I would start reading bytes off of it, and then making sense out of where value and IDs are. But then again, I need to have some sense, like the execution engine needs to have some sense of what metadata is. Like if you don't have that, my email field can go up to maximum this characters, then you cannot make sense that where I need to stop. So you need to define your offsets well. Like you need to first read the metadata table and then figure out that how many bytes I need to read. So let's talk about word alignment now. So this, apart from database system, this is a very famous problem that your CPUs are designed to fetch words from the RAM. So your system might be designed for 4 byte words, or it might be 8 bytes. But what I'm saying is that at any given moment, you can fetch values at an multiple of 4. So let's assume I have a 4 byte system, and I am saying that my CPU can go at a time and can read data in the multiples of 4. So if I'm saying that I have some data, let's say we have this byte array that is of 7 bytes. Uh, that's 8. Let's say I have 7 bytes, right? This is my first, second, third, fourth, fifth, sixth, and 7th byte. Now, what I'm saying is, if I tell my CPU that I need to fetch these 4 bytes, then it would have no problem fetching them. But if I'm telling it that I also need these 3 bytes, then in the older version of CPUs, they would throw you a exception that you cannot do this. But in modern systems, what it does is it does a two fetch writes. It goes and fetches 1, 2, 3, 4, and then it does a fetch instruction again. That it goes and then fetches 5, 6, 7. But along with 5, 6, 7, you're also getting some extra byte which the CPU is dropping eventually because that might not be in your address space as well. But uh, in modern systems, any structure you create in memory that should be word aligned. What I mean by word aligned is that assume your system is 32-bit words. That's 4 bytes. The 4 bytes I was defining before. So assume your system is 32 bit word. Your CPU can go ahead and fetch 64 bits at a time, not at a time, but your data should be aligned at 64 bits. So you cannot just jump in between and say that I need this particular data from that particular data. Like I cannot go and say that I need data from 13th bit to 23rd bit. I need to fetch this whole 64 bit into the CPU cache, and then I'll drop the extra things and just CPU will have to do more work for that. But if your structures are beautifully word aligned, then your CPUs will just have to do one read and it can get a ton of data for that. So while we are designing a database system, we will also ensure that when we are just writing out to disk, right? So unsigned character array, we are just dropping out to the files. But these files will be fetched into the memory and read by the CPU. So it would be better that if we could somehow make our make our tuples word aligned. So if we write a tuple and make sure that it is word aligned, then when we bring it to memory and our CPU reads it, then it doesn't have to do two fetches for one. That should be a one fetch. So in older system, they were like in older CPUs, they would throw you an exception that your system is not like your structure is not aligned. But in modern CPUs, they just go ahead and do the fetch instruction for you again. So they abstract away the stupidness that you're doing and just fetch it for you. But we will make sure that in our database system, our attributes in the tuple are word aligned. So, okay, let's just jump to the end of it. It's right there. Okay. So now if we look at this, we have a table foo which has a ID, which has a C date, creation date maybe. Then we have color and then we have a zip code. So now ID is 32. Yes, ID is 32 bits. So it covers up to this. Then we have a C rate that is 64 bits. So what happens is it extends to two words. So half is here and half is lying here. Then we have a color which is character 2. So I mean it has two, it is of its length is 2. And then you have a zip code that is again 32 bits. So it expands again. Now, if I do this, if I ask the CPU that I need to jump to some offset that let's say I need to fetch the creation date, then what CPU will do is first it will fetch this particular word, trim off ID, and then it will just maintain it in one of the registers. Then it will read this second word, trim off the C and the half part of zip, and store this particular thing in another register. And then it will just concatenate the two to form a 64-bit C date field. But that is more work. Instead, if I could have somehow I could have aligned these things so that uh, in one fetch I could read the specific field that I needed. So there are two ways to do this. Either you can reorder the fields. Most of the GCC compilers and other compilers do that. That if you define a you define a structure, then if your fields are not aligned properly, then they would just pad the remaining space with zeros, or they would reorder the attributes so that they are word aligned. So yeah, this example shows that if I want to fetch C date, the creation date, then how it would work. So now this is the first approach, that what you do is you pad anything that is not word aligned with zeros. And at the time of a fetch, you drop the zeros. So now the benefit with that is if I'm asking for the C date, I can just fetch it in one go. I don't have to do I don't have to do two reads for that. And if I want to fetch C, let's say, then I fetch this whole word, I trim this off, but I still get C for free. I just get C in one go. I don't do two reads for that. Even if I want to fetch the zip code, I read this whole word and I trim off these two. I still get it for one read. So alignment is basically you don't have to do extra work like doing two reads and then keeping the partial and then concatenating them. You just do a one read and you get the whole value. There might be some overhead for that, like I'm storing extra bits here with zeros, I'm wasting space. But then it's like no free lunches here, as Andy says, is that in computer science you don't get free lunches. You have to make a trade-off that either you're compromising with speed or you're compromising with the storage. So the another thing you could do is you could reorder the fields. So arrows are shown, but the final result is something like this. That in the original structure, the C date was first. I mean, it was behind the color and the zip code, but in the reorder structure, you have the zip code, then you have this creation date, and then you have the color, and then you have just padded out the rest of it with the 64-bit words. Now you have aligned this and you have packed it well. So in both these cases, we are occupying three words, that is 24 bytes. But there might be some cases that when you reorder things, you might not need padding and you might not waste space at all. But instead, you would reduce space. Like you won't need padding, and the space you might be using in padding would be significantly reduced by reordering itself. But what reordering does is it also needs to maintain some metadata that I have reordered fields, because the the end users, my application, is expecting that whatever declarative SQL I have given, I would eventually expect my data to come back in that form. So internally, if I'm doing this reordering, internally I would have to maintain the metadata that I have done this, and while pushing results back to the user, I have to reorder things in the way the user was expecting. Because if I start throwing out data that is not expected, then my clients might complain. Okay, so this was about word alignment, that while storing tuple, what you need to take care of. And let's talk about the tuple data itself now. Now, each attribute can be of different types. So it can be a variable character, like it can be a string, it can be integer, it can be a float, it could be a timestamp, it could be an interval, depending on what your database system supports. So like Postgres has a ton of different data types. So I think it has blobs also, timestamps, then enums, then you could do strings, then you could do integers, then you could do decimals, numerics, and yeah, there are a ton of basic data types that the database supports. So, usually in systems, whenever you define an integer small int or tiny int, that is like 1 byte integer or 2 byte integer or 4 byte integer or an 8 byte integer, you usually get what standard libraries give you. So if you're writing your system in C or C++, and you implement your integers for the database system, what you would do is, as your language provides the bytes for you in the RAM, like when you define integer A, if I'm doing this, the byte representation of 3 in the RAM would be exactly what you are storing on the disk. There might be NDNS issues in that, but you are not maintaining extra infrastructure to do this. So if you are doing additions, A plus B, on the data types of the database system, it is equivalent to just reading data out from disk formatting it into the data type of your language. So like let's say integer, and then just using the CPU instructions to just add them. So you're not maintaining extra overhead or extra data structures to emulate what a integer is. So uh, I wish I could have a better analogy for this. So let's take a example of big integers of Python. So big integers do is they maintain extra classes so that whenever your integer overflows or becomes larger than 64-bit, then you maintain that extra infrastructure to just to give you the illusion that you're still working in integers, but internally you're dealing with objects. You're dealing with heap objects. You're not dealing with integers, but you're dealing with heap objects that are internally using integers to perform the calculations. So usually in database systems, you try to do something like that, but not with basic data types. So basic data types like integers, big int, small int, and tiny int are usually what standard libraries provide you. The the all the other systems, like all the other data types, floats, variable characters, and blobs, timestamps, they're not standard. So you always have to maintain structures for these. So let's take an example of float or decimal values. So whatever your standard library gives you on the RAM, like how it is storing the exponent and how it is storing the where the floating value is, won't be the same representation that you are getting on disk. So for the disk, I am my database system will internally write structures and code to maintain that structure, to maintain the floating point representation on disk. It might take some inspiration from what standard libraries do and how you are getting floating point representation on the RAM, but it might not be exact because on the RAM then you have inaccuracies also. Like if I represent 0.3, it won't be exactly 0.3. So on the RAM it is okay, but when you are writing a database system and this system would be run in financial institutions or or in like mission critical systems, then you cannot expect these minor errors because like imagine like if this thing compounds on and eventually some money gets deducted from your account, you would panic, right? So the bottom line is that for maintaining all the data types in the database system, you have to maintain some structures. So you have to write your own code and define that how you want to store your data types on disk. That is not the case with integer types because they are simple. You just read them out and just use the CPU instructions for doing that. Even the operations on float, like addition, multiplication, and subtraction, those are not the standard CPU instructions you're doing, like MUL, that's for multiplication. And then I think there's a divide operation also on some CPUs. But for doing that on complicated structures like floating point numerics and floating points, you don't use the CPU instructions. You define your own emulation logic in the database system. So, so as this line says that if you're using native C++ types, then in variable precision, you might get some error, rounding errors. And there are types that are typically faster than this line. I don't know the meaning about though. These types are typically faster than fixed precision number because CPU and I have instruction registers to support them. I'm gonna have to get back on this. So this is what I was talking about. Like if you're writing a C program and you are just taking zero point 0.1 and zero point 0.2 and you are adding them up and you're printing the floating point representation of that, you would to some decimal characters you would not figure out that yes, there is some inaccuracy in this. But if you extend and you say that I need the trailing 20 digits of the floating point representation, then you would start seeing that there is not an exact representation of zero point 0.3. That is an approximation. Why is that? That boils down to how floating point is represented on the in the system, and they cannot maintain the powers of twos. But yeah, that's a different topic actually, and it's not for today. So we're gonna skim right past through it. So all I'm saying is that on the floating points need to be represented, need some code and some structures to be maintained in the database system. So let's read about fixed precision numbers now. Numeric data types with potentially arbitrary precision and scale used when rounding errors are unacceptable. So numeric and decimals, that's what Postgres supports in case of fixed precision, and in variable precision would be floats and doubles. So now, many different implementations store an exact variable length binary representation with an additional metadata. So that's the additional structures and that I'm saying, that you need to maintain some extra metadata, that where the, let's say, where the exponent is and where the floating point is, and uh, like if I update the value, what the floating point has moved to. So you need to maintain this higher level structure to maintain these basic data types on your database system. So this is a representation of Postgres numerics, that it is a C, Postgres is written in C, and this is a C struct. That this is the extra structure that I'm so talking about. That to support numerics, you need to maintain this in-memory structure and write this structure to out to disk, so that you have an exact representation and you don't have inaccuracies that your CPU instructions are providing or CPU data types are providing. So you maintain this. So this is a computational overhead, obviously, that CPU instructions must are much faster, but you have to do some, there's no free lunch again. You have to do some trade-off, that I need accuracy or I need speed. So this is a structure that stores the number of digits and the something known as a scale factor. Then it stores the sign, that is a positive or a negative, and then it stores something as a scale factor, weight of the first digit. And okay, so this is something. And you have a character numeric digit, and I think it would be a linked list of it. So it would store it as one digit after another or something. But the point is that database systems need to be accurate, and they need not rely on the CPU instructions or the CPU data types to perform their operations, which might be slow, but it's okay because we need accuracy. If accuracy is the trade-off, then you might consider using CPU instructions or CPU data, the native data types that your hardware supports. So Andy was giving an example that this particular code is just to add two numerics in Postgres. That assume I'm writing a program in C++ and I'm doing addition of two doubles. I would just write it in three lines. That integer double A is equals to this, double B is equals to this, and just print C out standard output to A plus B. And but in Postgres, you have to write all this code just for addition, just for numeric addition. That you have to cover edge cases, and then you have to see that you're not overflowing anywhere, or you have to see that if you are adding, then you need to maintain the precision, but you cannot rely on your system's native data types and instructions to do these. So this is a overhead for database systems, but it is an acceptable overhead. So tuples. Tuples always have nulls. Your some columns might not be nulls, like it would be compulsory. Like if you are defining a primary key, it should not be null. But null data types are there. That not everybody has a, let's say, not everybody has a last name. Yes, I do know some people that don't have a last name. So yeah, not everybody has a last name. So if you're storing a column name last name, you need to keep it optional. That yes, you might not store last name. Okay, so null data types, and what is the So we have three approaches of storing null data types, like what columns are null. So the first approach is that you keep a header, null column bitmap header, that you're keeping in the header, store a bitmap in the centralized header that specifies what attributes are null. So if we look back, mm, where is that header slide? Hold on. This. So if I store an array and assume that I have some number of attributes, and I store zeros for nulls and ones for not nulls. So when I go about scanning the values, like scanning the bytes, I first look at the null bitmap array, and then I figure out that this particular value is null and this particular value is not null. To talk about trade-offs, you just store a bitmap array in the header and the tuple header. So you'll have this array for every tuple because tuple has attributes, and you need to store this null attribute array in the header. So this is a common approach in row stores. That's the second line, and the most of the row stores do this. And then you have another approach where you could store special values. Like if I'm saying, let's say I have a, let's take this example that I have a column named amount, and I have defined it as an integer. And I'm saying that anything that is integer 32 min, that is negative something something. Uh, I think it starts with 4 or something. But anything, if this value comes up, I assume that it could not be inserted by the application, like my client, my user, but it is an internal bookkeeping for me that this is null. For that, I'm expecting that not my users and my clients are not inserting these values. This is me, the database system, that is keeping this as a tombstone that this is null. Not tombstone, like a, let's say tombstone. This is a tombstone that this particular value is null. So if this is my tuple and this is my ID, let's say, and this is my amount, this is always going to be 32 bits because I'm defining an integer. There might be a lot of values, like there might be 10, 20, 30, 40. But whenever I see an integer 32 min, I'll assume that is null. So I will give the execution engine will give back to the client, to the users, that this particular column is null. You might do this, but then again, this is an extra overhead for space, that you are still, the value is null, but you're still storing a 32-bit thing for that. You're still storing a 32-bit, you're still storing 32 bits for that. So in the first case, you might choose to not store it because you have the metadata. So assume you have the metadata and you know what schema my table is following. And you have this null column bitmap header that you read that array. And then you go about mapping this one to one. So what I'm saying is, this is my schema of columns. This is my C1, C2, C3, C4, C5. And this is my null bitmap array, column bitmap array. 0, 0, 1, 0, 1. Okay. So, and this is my actual data. This is my tuple. This is my header. This is my ID, let's say. And this is my values. This is my data actually, which I need to interpret. So what I could choose is that for every zero in the bitmap, I would just skip. I could just skip that particular thing and move on to the next one. So let's say column one, and assume I'm writing that particular one tuple I'm writing, and it follows exactly this null sequence. That this is null, this is null, this has some data, this is null, this has some data. So for data, what I'll do, I'll not store the anything for the first. I'll just start from this. I'll store this, let's say it's 32 bits. And then I'll store this. Let's say it's 32 bits again. That's 63, I guess. So I've stored these two, but now I have the metadata while interpreting the table. So, and when I read this particular tuple, I look at the header and read that this is null. So when that is null, I'll know that I need to give out null. So I don't need to read. So I'll just keep on iterating till I reach this. Then I read how big this is. Then I read 32 bits. Then I go ahead. Then this is null again, so I don't need to do anything. Then I find one again, and then then I read the next one. So this is the null column bitmap header might save you space as you're not storing anything for the nulls in the data section. But special values, you're still storing some data in the data section, and that's wasted. Although that is a marker for you to assume that this is null, but it's still wasted space. Then there is a last approach that is per attribute null flag that whenever you store a attribute, you're storing a flag, 1 bit flag, 2 bit flag, depending on how you're designing it, that this particular value is null. But then again, assume that you have tons of tuples, like 100,000 tuples you have, and for each tuple, each attribute, you're storing one extra bit. And if you go about storing that one extra bit for each attribute of each tuple, you have 100,000 tuples. And assume your tuple has 10 columns, then those 100,000 become a million. Yes, that become a million. And for each million, you're storing 1 bit. So that's 1 million bits. So that's a lot of wasted space. So yeah, Andy said that this is a wrong approach. You don't need to do this. But this is just to put it out there that you could do this. So this is a paper by CMU. Like this was written by students at CMU. Like I think yes, Andy was himself author for this, sub-author, and he wrote it along with some other professors of some other universities. But they talked about how you should store nulls. Like they have a specific paper for nulls only. So yeah, you could look at that. I have not read that though. Then let's talk about large values. That how do you store large values for tuples? Like each tuple might have a varchar that is 100 characters, 200, like 1,000 characters, assume. And assume you are also storing blobs. Blobs are just you are saying that I'm storing this file, but rather than uploading it to a S3 or to a storage bucket, I'm telling my database to store it for me. You should not do that though. Just if you're storing files, use a dedicated bucket like data bucket, but don't store your files on database systems. But for storing large content, like let's take the example of Wikipedia. You have ton of articles, and those articles have characters, and those varchars are long. How do you store them? So uh, you don't embed large to you don't embed large data in the pages, but what you do is when you're writing tuples out, if your data exceeds, you store a overflow page, you write your data to that overflow page, and then you contain a pointer from the tuple. So what I'm talking about is this. Assume this is my tuple, this is my text, and assume instead of this, I have a very long text, like I have ton of characters, like 10,000 characters, and I need to store it. So what I'll do is I'll allocate a page. It might be a large page also, because that might also boil down to your write and read trade-offs. But I will allocate a overflow page. This is my OP overflow page. And instead of storing the text in the embed the text into the tuple in the page, I'll just store the pointer to this particular page. That if you need to read this, you need to chase the pointer and read that particular page. So Postgres uses something known as a toast. That is the oversized attribute storage technique, I guess. I'm not very sure, but it uses something known as a toast to store oversized attributes. And MySQL and SQL Server, they follow overflow pages. And with overflow pages, you also have a lot of optimizations that you can follow overflow compression. That if you have a like if you have a large text and you're storing it in overflow page, then you could compress those overflow pages into small pages. And given that how frequently you are reading them, you could decompress the page in memory and just bring it back to life. So this is what I was talking about, that instead of embedding this, I allocate overflow page. Then I have varchar data into this. And then instead of storing that, I just store the size and then I store the pointer to the overflow page. And then there might be a chain of overflow pages. Like my text might be large, that might not fit into one page. You might allocate bigger pages for that, depending on if your system allows it. Like if you have to take a ideal world scenario, Oracle would allow it because it's an enterprise system, but I don't think they do it either. So you maintain an overflow page, you maintain a pointer to the overflow page, and when someone comes along and reads it, it goes to the overflow page, and just depending on if it is compressed or uncompressed, you read the data out. So blobs. So blobs. If you're storing blobs, then you might if you're storing blobs in a database system, you might have a very specific use case, or you're doing it wrong. If you have a very specific use case, then it might be justified. But if you are generally like if you don't have a very state-of-the-art system and you are storing blobs just for for the fun of it, you are definitely doing it wrong. So Oracle supports something known as a B file as their analogy to blobs, and Microsoft stores something as a file stream. So what they do is they also maintain pointers and they store this external file in their separate location. They don't embed that particular file in the tuple itself. They also store pointers. This is the same technique as the overflow page, but in overflow pages, you would just append text. You won't append files that are thrown at you. So the database system cannot manipulate the content of the external file, and there is no durability and transaction protections for these files. So what I'm saying is that uh, if I'm inserting a blob, then the maintenance of that blob is the responsibility of the database system. But if I am saying that I have this external file and I store a pointer to this external file, not via the database system, I'm storing it myself, that I have uploaded it to S3 and now I'm storing the S3 link in that. Then the protection and durability of that particular file is not the responsibility of the database system at all. Because obviously the database system just knows about the links. This is a small argument. So, this is a paper. You might read it. To blob or not to blob, large object storage in database or a file system. So that's an argument of like, should you store large files in database systems? You usually should not. Database should just store data. And if you have files, you need to store it in a S3 bucket or a Google bucket or something else. Finally, we are at the end of our the first lecture key slides. So these were the slides of presented in the first lecture, and we took like five videos for this, and now I'm putting these videos out to my blog also. Hopefully, no one reaches that blog, but uh, if anybody's watching this, then yeah, this is just the starting, so bear with me. Not very professional. Uh, Yeah, so next time, so this is the conclusion that database is organized in pages, and then pages might be organized. And then there are different ways to track pages, indexes, you could have heap file storages, tree file storages. Then different ways to store pages itself, that heap files and the tree files. Different ways to track pages are that database directory and the indexes, that what kind of indexes you are maintaining. Different ways to store tuples, that how you're storing null maps, how you're storing headers, and what approach you're taking, how you're reordering your words, how you're reordering your tuple like data. For that, how you are manipulating your metadata. So that's what we talked about. We're talking about file databases as files. So this was in the slides how database management system represent data as files on disk. In the next, we'll come to how it moves memory back and forth from the disk to the main memory and from the main memory to back to disk. So yeah, that was the end of it. And I don't think there is any demo left for this. So next time we'll just continue with the next lecture slides. Thank you for watching.